we're going to take a look at the idea of what an infinite series is in this section. And basically, for the rest of this large section that we're going to be looking at, we're going to be taking a look at infinite series, and we're going to determine what they're used for. And we're going to talk about if they actually lead to a finite value or if they lead to some divergent value. So we're going to first define what an infinite series is, and we're going to understand why we use them in mathematics. We're going to define convergence and divergence, and then we're going to take a look at two different types of series. We're going to take a look at geometric series, and we're going to take a look at these things called telescoping series. All right, so those are the big ideas that we're going to look at in this section. So in the previous section, we looked at sequences, and we had something like a sub n equals n squared. All right, all we're going to do now is we're going to take a look at a series. All right, so this is the difference between a sequence and a series. A sequence is going to be the pattern within a series. A series just means that you're going to add the terms up. So when you see this symbol right here, that just means sigma means to add the terms up. All right, so for instance, if we had the series n equals 1 to 5 of n squared, what that means is that we're going to square each of the 5 integers, and we're just going to add those up. All right, so this is the only difference. So if this was a sub n equals n squared, that would be 1 comma or 1 squared comma 2 squared comma 3 squared comma 4 squared comma 5 squared. But with the sum or the series, that means that we're going to add those values up. All right, so that's the difference between a sequence and a series. All right, now you might be wondering, okay, well, why would I ever want to add up all of the terms within a sequence? And what we're going to see later in the course is that these infinite sorts of series, all right, so this is a finite series, but an infinite series may represent some functions, all right, that we're going to be looking at, all right? So now sometimes they add up to a specific value, and we call that convergent. If they tend to go towards a number that reaches infinity or goes towards infinity, excuse me, that means that the series is divergent. Okay, so divergent means that we get to a number that tends toward either plus or minus infinity, all right, as we keep adding up the numbers or the terms of the sequence, all right? So let me show you an example of, and this is just basically big picture stuff, okay? So where do we use infinite series in mathematics, all right? So think of this infinite series, or I'm sorry, think of this finite series, okay? So 1 over n factorial, and maybe the first 8 terms of the sequence, okay? We're just going to add those up. So we get 1 over 0 plus 1 over 1 factorial plus 1 over 2 factorial. And by the way, 0 factorial, I know we didn't define this in the previous video, but 0 factorial is always equal to 1, right? If I add up these terms, all right, the first 8 terms in this sequence, that ends up being 685 over 285, which is not really a number of much consequence to most of us. And if we approximate that, that number just happens to be 2.71825, etc. All right. Some of us might recognize this to be close to the value of E. All right, and E is 2.718, etc. All right. Now I want you to keep this in mind because I'm going to use Excel and show you what happens as we keep putting in more terms. Okay, so let me go to Excel, and we're going to start at 0. All right, I'm going to do the first 3, and let's just drag this, and I'm going to do like maybe the first 25 terms. All right, that would be pretty difficult for us to do by hand, right? And so that's going to be equal to 1 over the factorial of the A1. All right, and then I'm just going to go ahead and drag this. Now, these are the terms in the sequence, all right? And notice that, you just keep getting like 10 to the minus 6, 10 to the minus 7, 10 to the minus 8, all the way down to 10 to the minus 26. So the values are really small. But let's add these up because that's what a series is. So I'm just going to add these numbers up, all right? And we already know that, remember before when we did this, it was like 2.718253968, all right? And then this time I just added in several more terms, all right? So check this value out. So this is going to be sum of the first 26 terms in a sub n equals 1 over n factorial. Okay, so that's what this really is. Now check this out. If I type in e to the first, or exp1, these two numbers are so scarily close that it can't be coincidence, okay? And if I were to go through and let me see if I can make the decimal places. So I'm going to format this, and I'll make the decimal places. Let's see, number, and let's see if I can go out. How many decimal places here? Right, so let's go out to like 30 decimal places, see what happens here. And then I'm going to open this up. All right. Notice that now, obviously, like Excel doesn't handle it past that. All right. But notice it's accurate to right here, which is probably somewhere like in the trillionths place. All right. If I were to count it out, that's scarily coincidental. All right. In fact, it's just not coincidental. It is purposeful. All right. So that's what we like to use infinite series for, is to represent these sorts of transcendental numbers. Okay. So these sorts of numbers that, you know, we don't necessarily know how these numbers arise, right? Except to be able to maybe use an infinite series. And of course, E is based on the fact that, you know, we take 1 plus 1 over n to the nth powers and goes to its infinity, all right? But this value can be represented by E. And eventually what we can do is we can represent functions with infinite series, not just specific values. So that's the whole purpose of these infinite series, is that we can represent more difficult sorts of algebraic and transcendental sorts of functions by using an infinite series. All right, now we're going to get to that later in the course, but that's the big picture stuff. All right. For right now, what we're really interested in is we're really interested in determining if the series are going to be convergent or if they're going to be divergent. And that's what we're going to be looking at right now. Okay, so we're going to be looking at these tests for convergence. All right. And really, it's almost multiple choice that it either converges or diverges. Now, to get any credit on your examinations, you're going to have to explain why it converges or why it diverges. There's going to be a lot of tests for these, okay? And they're not difficult algebraically, but a lot of times that these series start looking alike, all right? And that's where we want to make sure that we understand like what the different series are as we go through. So my recommendation would be, if you're not printing out the guided notes and using these to take notes on, is to maybe go through and just have like a separate paper that has all the different types of series. All right. So for instance, in this section, we're going to first look at geometric. And then we're going to look at these telescoping. Okay. And then after that, we're going to be taking a look at P-series and integral sorts of tests and tests for divergence. So what would be good is to maybe have a list of these different types of series tests as you're going along. All right. So in our next videos, we're going to start taking a look at our first type of series test, which is going to be looking at geometric series. And then after that, we're going to be taking a look at telescoping series. But that's essentially what we use infinite series for.